moment, we don't know how to set them. They're just empirical parameters. And it's well known that if some of those parameters were even slightly different from their known values, then there could be no life of any sort in the universe. I'll just give you a simple example. The neutron is about 0.1% heavier than the proton, which means isolated neutrons decay. If it were the other way around, if you twiddle the knob a bit differently and protons were a bit heavier than neutrons, and the decay went the other way, there'd be no protons in the universe, and no protons, there'd be no nuclei, there'd be no atoms, no chemistry, no biology of any sort. So you see just on that, which way did the knob go, so the existence of life hinges. And so Rees and others are enamored of the idea that maybe these knob settings are just randomly distributed throughout this multiverse, this collection of cosmic domains, and the fact that we live in a universe so well suited to life is the reason we see the laws of physics we see is because that's the life-encouraging set of laws. So this is a very fashionable point of view. Sometimes called anthropic selection, though nobody suggests it's got anything to do with human beings as such. Now, another advocate of this point of view, Lenny Susskind, one of the founders of string theory and the person who has most stressed the fact that there are this vast number of low-energy solutions of string theory, 10 to the 500 I've got somewhere, explains it as follows. A megaverse full of pocket universes that have bubbled up out of inflating space like bubbles in an uncorked bottle of champagne. So this imagery that there isn't just one universe, but a stupendous, well, maybe an infinite number of universes, but with a stupendous number of possible bylaws characterizing them. And this becomes most explicit with the model of eternal inflation due to Andre Lindy and Alex Vilenkin. That is just a schematic diagram that the universe that was, our universe was born in a Big Bang as some sort of quantum event, but these quantum events are carrying on throughout space and time. So there are not just one Big Bang, but many Big Bangs, and each of them gives rise to a universe. Because these are quantum events, they explore the landscape of all possible low-energy string theories, low-energy solutions of string theory. In other words, all possible universes get made by this mechanism. And so a lot of my colleagues who like this feel that we've now reached the end of the road, that we can explain the universe and explain the laws on the basis of this sort of cosmic selection principle, that we have a multiverse of all possible laws out there, and that the one we observe, we explain the laws that we do, so we answer Einstein's question, could the universe have been different? The answer is yes. Why is it as it is? Because we're here to see it. And they feel that that is the last word on the subject. But I think it's very far from the last word. I think it's a very incomplete explanation for why the laws are as they are. And the reason is that it really shoves the problem up one level, because in order to make this multiverse theory work, for example, eternal inflation combined with string theory, we have to invent meta-laws in the multiverse. Instead of laws in the universe, we now have meta-laws in the multiverse. For example, we need a universe-generating mechanism. Lindy's mechanism for doing it is very explicit. It depends on general relativity and quantum field theory. So these have to be assumed as somehow given. They are imprinted on the multiverse in the same way that we thought of laws as imprinted on the universe. And there has to be some sort of super law and symmetry breaking, for example, the string theory Lagrangian. There has to be a space-time manifold for the action to be played out, and a whole bunch of other stuff that is imported. In other words, there's a lot of intellectual baggage that goes in to a multiverse theory of multi-laws. And so we can ask, once again, where do these meta-laws come from? Why do they have the form that they do? And do they exist reasonlessly? I should say that if the laws of the universe have no reason for why they exist or for why they have the form that they do, then in the philosopher's sense, the universe is ultimately absurd. Because if something exists for no reason, we say it's absurd. Now, it could be that the universe is absurd, or that the multiverse is absurd, and that we just have to accept that. But the whole of science proceeds on the basis that there are reasons for why things are as they are, why things happen. And if you abandon that principle, then are we doing science? And so science is a curious thing. So we've got a logical explanation, chain of explanations all the way down until we get to the laws. And at that point, people want to do a backflip and say, oh, well, they don't exist for any reason. So the question is, can we come up with a system of thought that gives reasons for why the laws are as they are? Now, this little diagram might be helpful or it might be confusing, I don't know, but it sort of charts the different possibilities. There are three subsets of the total set of all things here. First of all, there's what can be observed. So these are all of those universes in the multiverse that can have observers, have inhabitants, if you like. So we observe our Hubble region, and there may be other regions out there that are observable, but there'll be a whole lot of other stuff that can't be observed, for example, universes that don't support life. So we've got this bigger set of all that exists with a subset of what can be observed sitting in that. And the boundary, the blue line that separates these two, is what can be accessed through this anthropic reasoning. We can say, well, the reason that these things get observed is because they can support life and observers, and that the things in the yellow region can't. And that seems fairly clear. I mean, it's a sort of trivial point. But it would be a mistake to think that that blue line is the whole story. There's a further line, the white line, which separates all that exists from all that could exist. What could exist but doesn't. All those things that might have existed, all those universes that may have existed but simply don't. And so this is, if you like, the ultimate question of existence. Why is it that some things get to exist and other things don't? Because we can imagine all sorts of universes, and if only a subset of those universes exist, then we want to know why, what determines that boundary be. So I call this the problem of the rule that separates what can exist from the things that could have existed but don't, what does exist from the things that could have existed but don't. Now, there are really only two natural states of affairs where this problem is dodged. One is that nothing exists, and I think we can rule that out immediately on the basis of observation. But the other one's a curious one, which is that everything exists. Maybe everything that can exist does exist. And that's the point of view that Max Tegmark, a cosmologist at MIT, has been supporting for some years. He said everything that you can possibly imagine, and all the stuff you can't imagine as well, it's all out there somewhere. Not only all universes with all possible laws, but universes with all possible mathematical descriptions, including bizarre forms of mathematics like fractals and so on. That they're all there somewhere. There's a universe for everything that you can imagine. And so he doesn't need to explain what it is that separates all that can exist, all that does exist from all that can exist. I don't find that many people like Tegmark's idea. I think most people have this point of view that less than everything exists. That there are some things that got left out. You know, in the existence business, some things got left out. So some things have been dignified with existence, and some things just didn't make it. And if so, then something must divide what exists from what can exist but doesn't. And Stephen Hawking has alluded to this in his famous book, where he says that what is it that breathes fire into the equations and makes a universe for them to govern? In other words, we can write down all sorts of fancy mathematics, but just like Mother Nature in the warehouse takes a shopping trolley and only takes out a few items. So to change the metaphor, Hawking says, well, some equations, get sort of dignified with the property of having fire breathed into them, and they correspond to a universe. And so we can inevitably ask, why those equations, why that universe, why those laws. Now, if we're prepared, so now at this stage all bets are off. We're trying to think how are we to possibly come up with an explanation. And I've made a list of what I call weird laws. So these are, we're relaxing this 300-year-old Newtonian point of view. Then we have a number of possibilities we might like to consider. The first of these is that the laws might depend on time. C.S. Peirce, the American philosopher, was ahead of the pack over 100 years ago, talked about time-dependent laws. Lee Smolin at the Perimeter Institute has recently tried to develop that in quite some length. Then there's a possibility of non-local laws. So these are laws that, instead of referring to space-time points, would have non-local interactions. Yakir Aronoff is promoting that idea. The possibility of global principles. So what I mean by that is things like Mach's principle or Penrose's cosmic censorship hypothesis. So these are things which are, they augment the laws of physics. They are additional statements which are important constraining factors in the world, but they don't derive from local laws of physics. We could consider laws not derivable from an action principle, and the biologist Robert Rosen has considered that. Time asymmetric laws, Prigogine was keen on that idea. Emergent laws, I'll come back to that. So John Wheeler and George Ellis have both promoted the idea of the laws as being emergent rather than elementary. Finite accuracy laws is the one I'm going to dwell on in a moment. Rolf Landau and Paul Benioff have both suggested such things. Statistical laws, maybe everything, as Wheeler has described it, comes out of higgledy-piggledy. And Holger Nielsen in Denmark has long promoted that idea. Then we have the possibility of laws of initial conditions, something that Hartle and Hawking and then Murray-Gell-Mann have spent a lot of time trying to formulate, and maybe final conditions as well, both initial and final conditions. So these would be laws that are quite unlike normal laws of physics. State-dependent laws, well, I've already been talking about how if the superstring, on the superstring landscape, if you're at a particular point on that landscape, you might have different low-energy laws. So that's a weak version of it. I'm going to come to a strong version in a moment. Getting even more bizarre, acausal laws. Pauli wrote a book with Jung, Carl Jung, the psychiatrist, on the notion of acausal laws, an acausal connecting principle. They called it synchronicity. So that the idea was that there were events at different space-time points might be connected in a way that was not the usual relativistic causality. Don't know anybody who's really done anything with that. And then we might have teleological laws. So these are laws that refer to some end state. And that was Aristotle's original idea for laws. And to some extent, D'Alembert's principle incorporates that, but in a hidden way. Or the extreme version might be no laws at all. There are no laws. Dennis Sciama, who I knew very well in the 1970s, seemed to think that maybe that was the case. There really aren't any laws. It's just the way we see the world. It's as everything is sort of anthropically selected. So we've got all these different points of view. Now I want to just focus on one, because I've not got too much longer. This quote from Laplace again. Let me go back to this point here. If this intellect were vast enough to submit the data to analysis. So Laplace has this idea that if you have this super-duper calculator, this demon, who has infinite resources, then the demon could predict in detail everything that was going to happen in the universe. But I think that this notion of a Laplacian demon is an absurd and completely unjustified idealization. It's an enormous extrapolation. And one of the people that thought the same thing is Rolf Landau. Landau pointed out that, to quote him, the calculative process, just like the measurement process, is subject to some limitations. A sensible theory of physics must respect these limitations and should not invoke calculative routines that, in fact, cannot be carried out. So Landau, because of his background in the theory of computation, thought we should think of the laws of physics not so much as, these God-given perfect mathematical forms, but more like software running on some hardware. And what was the hardware? Well, none other than the great cosmic machine. So his point of view was that if you can't actually carry out a calculation in the real universe with its real resources, then we should not invoke it as a description of the universe. So we shouldn't use any mathematics that can't actually be, in principle, done within the universe. So why is the universe limited in resources? Well, Seth Lloyd at MIT pointed out that for a universe of finite age, if we think of our region of the universe beginning in the Big Bang, there's a causal horizon beyond which we can't see. So 13.7 billion light years is the size of it today. And this means that the volume of space within that horizon can only contain a certain maximum number of bits of information and can have only processed a certain number of bits of information since the Big Bang. And that number is 10 to the 122. That's a lot of information, but nevertheless it's finite. So it comes about, this is just a picture that shows where this comes from, and it comes from just applying the fact that there is this backward light cone and gives us a horizon, and then one can apply just basically thermodynamics and quantum mechanics to come up with this limit. So it's it's not a difficult calculation. You get the same limit, incidentally, from a somewhat different argument that we now know that the universe is dominated by dark energy. So there'll be another sort of horizon in the universe, an event horizon, which coincidentally is about the same size as the particle horizon. And if you divide the area of the event horizon by the Planck area, you come up with the same number, 10 to the 122. These ideas have been formalized recently by something called the holographic principle, which simply says that all of the physics that occurs in a volume of space can be encapsulated by the information contained on a surface that surrounds it. So the maximal surface, in the case of, say, de Sitter space, the universe dominated by dark energy, is to take the de Sitter horizon and divide it by the Planck area. And you come up with that same number. So the conclusion of this, then, is that the universe has finite computational resources. And that represents a fundamental cosmological limit. A cosmological limit on what can be known in the universe. The total number of bits of information in the universe is limited to this 10 to the 122. So it limits what can be known. So it's a curious principle because it's in addition to quantum uncertainty and Turing uncertainty. This is a sort of cosmological uncertainty. And notice it changes with time. The universe gets older and the horizon in our past gets bigger. We can know more. But nevertheless, what we can know is limited, a finite number of things. Well, I mentioned Peirce and I've mentioned Wheeler. Wheeler's point of view is that there is no law except the law that there is no law. He said he wanted everything to come out of higgledy-piggledy, and he took the point of view that the physical conditions in the universe just after the Big Bang were so extreme that we could not assume that the laws of physics would apply, and that these laws somehow emerge like a picture coming into focus as the universe evolves away from that. And I've been trying to flesh out that idea. Here's another quote from Anton Zeiling: other laws we discover about nature do not already exist as laws of nature in the outside world. So here we have physicists taking this heretical point of view that the laws are not Platonic, God-given, transcendent, immutable, and imposed, but they're somehow inherent with, inherent in, and emergent with the universe in the Big Bang. So could it be the case then that this notion of, if we take Landau's view, that we should not invoke laws of physics that cannot in principle be calculated, so if there is a finite precision, finite number of bits in the universe is a finite precision to any calculation that could in principle be performed. In other words, Laplace's demon will either, if Laplace's demon doesn't inhabit a Platonic realm, if Laplace's demon is in the real universe and has to use the real universe to compute, then obviously there is a fundamental limit to what can be computed and what can be predicted. And so the question is, does it make any difference? 10 to the 122 is a really big number. Now, for almost all practical purposes, of course, it makes no difference. So let's take a typical law, the law of conservation of electric charge. We can check that law to about 10 significant figures. Of course, it's very famous, but there's still plenty left over. Nobody's going to test that law to 122 significant figures. So if we were to say that the laws of physics have only finite accuracy, they're fuzzy to the level of 1 part in 10 to the 122, it won't cause any problem for that particular law. But there are circumstances in physics, circumstances involving exponentiation, where we come up against that number in a very brutal way. And one of these, very famous one, this is Hawking's explanation of black hole radiance. So Hawking, of course, famously predicted that black holes are not black but emit heat radiation, and this was the construction he used in 1975 to demonstrate that. I won't dwell too much on the details. It's a calculation in quantum field theory where you take a Bogoliubov transformation connecting the modes in the in region down here with the modes in the out region up there, and this is the relationship that connects them, and you see that there's an exponential factor in the modes. Now, this is easy to understand. It's when a star implodes to form a black hole, a source of light on the surface of the star fades out exponentially fast. The E-folding time is about 10 to the minus 5 seconds for a solar mass star. And this is an exponential redshift factor in gravitational collapse. And so after 1 minute, it's e to the 3 million, you see, in here. Now, in order to carry out the calculation, Hawking had to do this Bogoliubov transformation over an infinite number of modes. So it was known at the time as the trans-Planckian problem. But we see it's part of a deeper problem. It's a problem that we have to take infinity seriously if we're to get Hawking's derivation of black hole radiance. But if we limit that to 10 to the 122, we don't get black hole radiance, we just get a little flash of transient radiation from the collapse, and we don't see the steady thermal flux. Now, does that mean Hawking is wrong and black holes don't radiate? Well, it may be possible to derive the Hawking effect some other way. But if you want to place that limit, upper limit, on that summation there, then it's true that we don't get it. So it may have real consequences. Let me finish with an example that's somewhat closer to home, an example that comes from quantum mechanics. The other place we hit exponentiation is quantum entanglement. If we have n particles, we can have 2 to the n possible states, and the power of quantum computation, if we should achieve it, rests precisely in that exponentiation. But of course, exponentiation implies that we will hit that limit of 10 to the 122 in pretty short order. 400 entangled particles already has a state that has more branches of the wave function, is the best way of putting it, than there are bits of information in the entire observable universe. So in other words, if I wanted to tell you how to make a generic entangled state, a particular generic entangled state of 400 particles, I would have to commandeer the entire universe to even specify that state, let alone to predict its unitary evolution. So this really forces you to make a choice. Are you a Platonist or are you not a Platonist? If you're a Platonist, you don't need to worry, because Mother Nature computes in this Platonic realm outside of the universe, in this transcendent heaven that derives straight from monotheistic theology. If you believe that, then there isn't a problem, because Mother Nature will have infinite resources and is not limited. But if you believe that the laws, like Wheeler and Landau, that the laws of physics are somehow in the universe and are like the software of the great cosmic machine, then it's a finite accuracy machine. And we cannot take seriously any calculations that involve numbers bigger than 10 to the 122, unless they're just put in for manipulation. Any numbers that correspond to real physical things. So there are not enough parameters in the universe for you to be able to specify a generic state of 400 particles. So does that mean quantum computers won't work? Is all the hype misplaced? Not necessarily, because when you ask people who are trying to develop quantum computation what they want to do with it, typically applying Shor's algorithm, then what they want to do is a tiny, tiny subspace of the whole of the Hilbert space. So I'm referring here to a generic property of 400 entangled particles. And what I'm predicting is that the unitary evolution of this system would break down, that this cosmological limit, this additional source of unknowability or uncertainty, would manifest itself through a breakdown of the unitary evolution if we had such a system. I'm pretty much out of time. I just really want to summarize by saying that this business of the laws of physics being depending on the state of the universe, it's the finite computational resources of the universe, restores this symmetry between laws and physical states that Newton took away. Instead of putting the laws off limits out there, unexplained, perfect, immutable, we're bringing them into the universe. And now we have the laws depending on the states, because as the universe ages and more bits of information are, so to speak, available, then this limit becomes less and less stringent. But in the early universe, would have been very significant. And I have conjectured that there may be relics, cosmological relics, which are from an epoch at a time when this finite bound would have been more stringent. So, but we see, nevertheless, that the laws, so to speak, depend on the physical states by sort of congealing in the manner that Peirce and Wheeler had in mind. But this seems to provide us with an actual mechanism whereby they do so. So this is a view of the world which is, I think, best described by the word emergence. So we have emergent laws and emergent states. And so now this is purely schematic, but we can think of a sort of joint space of states and laws, and imagine that the observed universe is something like an attractor in that joint space. And so we have, this is what Wheeler always wanted, a sort of self-synthesizing, self-explaining reality, a closed loop of existence, he called it, where life and mathematics and physics and the universe somehow are all mutually interdependent in that way. And so I want to finish just with another emblem. You'll all be aware of the story about the lecturer who stands up like this and talks about how the universe is put together, and then is challenged by a woman at the back who says, you may be very clever, but I know how the universe is put together. And the lecturer says, pray do tell me. And she says, well, it's the Earth is standing on the back of an elephant, which is standing on the back of a turtle. And so the lecturer then replies, well, what is the turtle standing on? And she said, you can't fool me, it's turtles all the way down. So it's a famous parable. What I've been telling you today says that if we don't want to get into an infinite regress, we have to stop somewhere with a levitating super turtle. And that for most of my career, most of my colleagues have believed this levitating super turtle are the laws of physics, unexplained, somehow holding everything else up. And what I'm saying is that after 300 years, I think that we can try other possibilities. And I've been telling you about the possibility that the universe somehow self-organizes its own laws and are emergent with the universe. And so that gives us a different sort of picture. This is the take-home message. A turtle loop, not turtle soup, but a turtle loop, a sort of self-explaining, self-consistent reality. And I think I now have run out of time, so I'll stop there. Thank you.
So let me ask you, are you saying that the laws have sort of condensed out?
Right.
Along the way.
There's the laws, even today, have a finite precision, but in the past they were less precise, and so it's like a picture coming into focus.
Right. So we should be able to find time dependence upon some of these laws.
As I said, there could be cosmological relics that reflect the fact that that this inherent uncertainty in the laws would have been larger in the past. So if you go back to the time of inflation, for example, then that number becomes 10 to the 20, not 10 to the 122. It's only 10 to the 20. And so that would limit the duration that we could make sense of inflation. You want to write down the laws of quantum field theory and so on at that time. There would be that additional form of uncertainty that might well manifest itself in departures from precise flatness, for example, in the universe. That's what I would expect, because 10 to the 20 is just about on the edge of getting inflation to do its work, but not quite well enough to give us very, very high precision flatness. So I would expect departures from flatness.
Do you have a question, Zach Levine?
So why 10 to the 122 bits rather than, say, 10 to the 122 qubits?
Right, so that's an absolutely fundamental point that, of course, comes up again and again. So I think it comes back to you have to take a position on the nature of reality. Again, if you're a Platonist, you can believe that qubits are real. But most physicists I know say that qubits are a way of calculating that anything that we actually observe is a bit of information, that we interrogate nature and the answer comes back to us in bits. And I embarked on this discussion by asking precisely that question. I thought to myself, well, black holes have this entropy associated with their surface area, but supposing we made a black hole out of entangled particles, couldn't we get exponentially more bits of information as a result of that? And of course was soon told by Bekenstein and Hawking and others, that at the end of the day what we observe are the bits, and